Hi all. Now we'll go ahead with our next topic, that is functional dependencies. So here in normalization, this functional dependency is required. So depending on these things only, functional dependencies. So is it normalized or not? Normal forms we study it. Okay. What is functional dependency? Is nothing but here formally we are going to measure the relation. Okay, so that is relation design, whatever we are doing it, is it good or not? For that we require functional dependency. So here functional dependency is nothing but is, suppose x and y, there are two sets. Okay, so set of attributes. Then we say as a set of attribute x functionally determines a set of attribute y if the value of x determines the unique value of y. Okay, if the value of x determines the unique value of y, then we say as a x functionally determines y. Okay, so this is what functional dependency is. This meaning is, suppose in your relation there are two tuples. If there are two tuples, okay, with same value of x, okay, so then it must have same value of y also. Okay, that is nothing but if two tuples t1 and t2 in a relation we have, that is if t1 of x is equal to t2 of x, that is nothing but two tuples x values are same. If this is there, means there should be t1 of y is equal to t2 of y. Then we are saying as a x functionally determines y. Okay, so we'll take one example now. So suppose consider as a, so one student information is there. Okay, so this is a table, one table. So student information we're keeping it. So here we have name, so before that also some attributes will be there. Here after that also some attributes is there. So his city we are taking it, then pin code number we are taking it. Okay, so these things we have it. So now I will say as a pin code number if I have, so I can determine his city. Okay, so I'm saying as a, if I have pin code number, so then I can derive, so in which city he belongs to, he or she belongs to in which city. Okay, so this is what I'm doing is, here just I'm putting the arrow mark, that is from pin code number I can derive this is city. So this is my x, that is pin code number is my x, then city is my y. Okay, that is nothing but I'm saying as a x derives y. So that is I can derive city if I know the pin code. Okay, so same thing can I say as a, if I know the pin code number, can I derive that person's name or that student name? No. Okay, so maybe in one city or one pin code number or n number of students will be there. Okay, so that we can't derive it. So here this pin code number can derive this city. Okay, so this is nothing but functional dependency. So here the city has the functionally dependent on pin code number. Okay, this city attribute functionally dependent on pin code number. So that is what we are saying as a x derives. So here we can write it as a pin code number. Okay, so normally I will write as a small pin code number. Okay, from this I can derive the city. Okay, so this is what we can do it. Okay, so from pin code I can derive the city. Mhm. So like this, if any attributes are there, so here I took as x and y. So x is nothing but here actually a set. Okay, so the set means it may have one attribute or more than one attribute, and same thing is y also. So it may have one attribute or more than attribute. So whatever example we took it here, in both there is x set and y set, we have only one attribute. So you can have n number of attributes in this set or in this set. Okay, or both can have a number of attributes. So like that, anything if it, a set of attributes can derive the another set of attributes, that will say as these are the functionally dependent on each other. Okay, so this is what functional dependency. So normally how we'll write is x arrow mark y. This denotes, so it's internally we are putting some kind of constraint on the our relation instances. Okay, so there may be some constraints. So here this nothing but constraint is there. If uh, city is completely dependent on pin code like this. Yeah, so the city name is whatever name we're writing is, that is dependent on pin code number. So like that we can say it. So in real life, whatever things will be there, those all things FDs normally will capture it. Okay, so I think so these are some examples. Okay, so in our company database system, if you saw, so from SSN I can derive that employee name. Okay, so if I have a P number, that is project number, so I can derive project name also, project location also, in which location it is. So this, these two together my Y here. Okay, here this side this is a X only. Okay, so and in one more table, if I have, say, suppose that employee SSN, then project number, so these two together I can derive how many hours that employees worked on that project. Okay, so that is here, this is my Y, only one attribute is there, more than one attributes are there in X side now. Okay, so like this any combinations will be there. So here X to Y, there is SSN, and if I given as a that project number, so from these two I can derive the how many hours he worked for that project. Okay. Okay, so here is the NFT is a property normally. Okay, so of an attribute in a relational schema R. Okay, the constraint must hold on every relation instances. Okay, so whatever we is told here. So in database, if I have thousands of rows, okay, so each instance, each rows follow this functional dependency. So it should be throughout for the all the instances of data, whatever we are inserting. Okay, so if k is a key, okay, so if I have one key in a relation schema, okay, that is a relation schema R, capital letter R. So in this, if k is a one key, so it means all other attributes in that table, okay, or in that relation, so will follow the functional dependency. It is nothing but, if I am saying as a key is nothing but indirectly we are saying as it's a primary key. Suppose here if I have as a roll number, okay, that is first student, if I have as a roll number, if I given as a roll number, can I derive his name? Can I get his name? Yes. If I have roll number, can I get other instances here? Yes. If I have as a roll number, can I get the city? Yes, we can get. If I have a roll number, can I get the pin code number in which city he belongs to? So like that, if I have this a primary key, suppose name roll number is a primary key, so I can get the all other remaining attributes values also. Okay, that is nothing but we can say as a from this key, so remaining all functional dependencies by default it will be there. Okay, so no need to mention that one. So by default you will be having the functional dependencies, that is from key to remaining all. So here we are saying as a from key. Okay, then key functionally determines all the attributes in her. Okay, by default it will determines all the attributes in this relation. Okay, so why this is key is little bit difference between key and primary key. So just we are saying that it's a key only now as of now, that we would differentiate will make it. Okay, then next one is inference rules. Okay, so there's nothing but already you will be having some set of functional dependencies. Okay, so from that set of functional dependencies, what we are going to do is maybe some other set or some other functional dependencies we can derive it. Okay, so those are directly or not mentioned in our database, and some are mentioned only. Okay, so from that can I derive some other functional dependencies? Okay, can I get some other functional dependencies? Okay, so those things, for that purpose some inference rules are there. Okay, so these already you studied in your mathematics subject also. Okay, so DMS. So here this is the first rule is IR1 inference rule. IR1. Okay, so what we'll say here is a reflexive. Okay, so here we are saying is if y is a subset of x, okay, then x functionally derives y. Okay, so here we are saying that y is a function subset of x. Okay, so we'll take one example in this one. Suppose, so here whatever things are there in this, suppose in my, yes, so suppose I have four things. Okay, so let me write as a B C D. These are the, yeah, four attributes. Okay, So my capital X, that is nothing but this one set of attributes. Suppose I have say A, B, C. Okay, three things I will take it. Okay, then Y. Okay, so what we are saying here is a Y is a subset of X. Okay, subset means among these only it will come. Okay, so suppose consider as a only. Okay, so here what we are saying is functionally. So then we are saying is a X functionally determines Y. We are saying it is nothing but if I given as a that is uh, in this tables a column value, b column value, then c column value, can I get a value like that? We are saying it. Okay, that is you have already a value, then again we are saying is it functional, can I derive this one a? Yes, already it's there, already you are only giving it. Okay, that is if I will repeat it once again. Suppose user is given as a that is a value also, b value also, then c value, that is three column values. Then he's asking us what is the a value, so already he is only giving it. Okay, so in that whatever is there, then you have to mention it like that. So if that is a y is a subset of x, then we'll say as a that is from x you can derive the this is y is a subset of x. Okay, so it means in the from x I can derive the y. Okay, so this is the functional dependency. Okay, this is the first inference rule. Okay, then second one is augmentation. Okay, so that is here x to y functional dependency you have. Okay, so then some set of attributes. Okay, z. Okay, that we're adding in the left hand side and right hand side also. So this holds good. That is nothing but you have some set of attributes here. From this you can derive the y. Okay, so one or two extra attributes you are adding inside a left hand side, so extra thing you are giving it. So and here also you are giving the same attributes, so then also functional dependency holds good. Okay, it will not change any of these things. Okay, then next one is transitive. Okay, so that is from x to y I can derive, then y to z I can derive. So it means from x to z I can derive it. Okay, so these are the transitive rules. So proof of these things I will not study. Okay, we will not study these things. Okay, so already you people have studied in discrete mathematics. Okay, so here x to y you can derive, so y to z you can derive it. Okay, so these two are there functional dependencies. Now we're saying is that from x to z you can derive it. Okay, so these two are the basic inference rules. Okay, so then so one more thing we have is there's a decomposition. Okay, so from x to z you have the functional dependencies. Okay, so here y is one set, z is one more set, x to yz you have functional dependencies. So then we can say as a just we will differentiate and we'll write it. Okay, so x to y we can derive it and x to z we can derive it. Okay, so this is a decomposition. Whatever right hand side we have, those are the set of attributes that we will derive into two different sets, that is y and z. Okay, so two things we'll write it. Okay, then union. Okay, so x to y I can derive it and x to z I can derive it. It means x to yz I can derive it. So here this is a functional dependency. X to y I can derive, this is a separate one. Then again x to z also I can derive it. Just we are combining it and we are writing now. So x to yz we can derive it. Then pseudo transitive. Okay, so here x to y is there. Okay, wy to z is there. So okay, so here whatever y is there, that instead of that y, so I'll write as a x. Okay, so there is nothing but here w to y, wy both together can derive the z. So y is already derived from x. Okay, so instead of y I will write as a x here, so wx to z I can derive it. Okay, so these are the extra things, additional inference rules. Okay, so next one we study is a closure. Okay, closure of set f. Okay, so here what is f is nothing but here set of functional dependencies in a relation, whatever will come, that we can write it inside a one set again. Okay, so that will say as a f. Okay, so if suppose here consider as a in this one, so I can say as suppose a to b functional dependency is there, suppose. Okay, then c to d is there. Okay, so like that some functional dependencies. So in diagrammatically normally we'll write as a here this is a to b, so a to d functional dependencies we have it. Suppose now what we are doing is just these things we'll write it inside a one shot and we'll give some name. Okay, this is a f. So here we have the a to b and c to d, two functional dependencies in relation. Okay, these two together we return and we are denoting by one set name, that is f. Okay, so now for this, that is the closure of set f of fds. Okay, so it contains fds is the first fd. Okay, it's the second fd. Okay, fds is the set f plus of all fds that can be inferred from f. Okay, so this is nothing but here closure of f is nothing but, so closure of, now I will write as here shortcut. This is a closure of f is nothing but, so whatever fds you have, these thing plus something you have to add it in this one. Okay, so what you have to add is something but whatever inference rules you can apply it and you can get the fds, those all fds you can add it. Okay, suppose here again I have as a, suppose here one more FT B2C. Okay, so consider as a previously only we had as a here. Okay, because now I am adding this is because we are not had any correlation between previous two FDs. Okay, so here now I have as a B2C also. These are the total three FDs I have. Okay, so this is my F. Okay, so whatever. Now F plus, that is nothing but closure of F. Okay, so it's nothing but previously whatever we have these three. Okay, so I will not write it here, these three comma extra thing whatever I can derive it from this one. Okay, so now if you saw a to b is there, b to c is there. Okay, so if, suppose if I apply transitive, okay, so transitive inference rule here whatever we studied. Okay, that is x to y is there, y to z is there, it means x to z I can get out. Okay, that is a to b is there, b to c is there, so I can get a to c. Okay, so this was not there in my previous fds. Okay, so in f set we are not had the anything, so here this is a to c I can add. So same thing I can add, b to c is there, c to d is there. Okay, so I can add b to d. This again transitive. Okay, now can I add a to d? Okay, that is a to c you have, a to c you have, c to d you have, then you can derive a to d. Okay, this also transitive. So like that whatever inference rules you can apply it, so maybe among these things three or these three, okay, including all these six, any inference rules you can apply it, then whatever fds you will get it, those also if you added, so those all things together will say as a f plus, that is nothing but closure of f. Okay, so previously we will be having the some FDs, set of FDs. So that we're saying as a F. So closure of F is nothing but apply the inference rule on each of these. Okay, or combination of these, then you will get the some other FDs. Okay, so these are the other FDs, extra FDs we got it. So these entire thing together, okay, these set entire thing together will say as a closure of F. Okay, then closure of set of attributes. Okay, so here whatever we studied with respect to this is fds, now we are saying as a with respect to attributes. So closure of x with respect to f in the set x plus of all attributes that are functionally determined by x. So now first was there as a, now a, this is considered as a x. Okay, so now this is my, okay, there is set of attributes, so whatever we are saying is a attributes, this is x. Okay, so here with respect to f, with respect to whatever we given starting here, this is f. Okay, is the set f plus of all the attributes that are functionally determined by x. Okay, so now previously here if you saw here my x was considered, this is x and y. Okay, so here x and y, so previously my x was this attribute name a. Okay, so from a how many attributes I can derive, so in this fd whatever given is b only. Okay, so here I had as a closure of x. Okay, my x is nothing but I am considering as a. Okay, so closure of x, that is x plus I will write it. So closure of a is nothing but, so how many attributes you can derive, this is okay. So from a, sorry, here from a how many attributes I can derive, that is b was there. Okay, now if I am that is here whatever we have b only. Okay, so now we'll apply some other inference rules, then we'll check it how many attributes I can derive it from a. Okay, okay, so here b to c also there, so from a I can derive B and C. Okay, so here if you added closure, we added, now we are seeing as a how many other attributes you can derive it. So I can derive D also. Okay, so those all things, if I have only A, so I can derive all these four attributes. Okay. That is, from A I can derive B, from B I can derive C. So it means I can derive from A, C I can derive it. Okay, so here A is there, B is there, then C is there. Okay, then if I have as a C to D also there. Okay, so that is also from A I can derive the D also. So these all nothing but here closure of A. Okay, small letter A, closure is, that is all the attributes A, B, C, D. Okay, so depending on the functional dependency, you will get how many other attributes you can derive it. Okay, so in detail we will study this one by taking the real example. Okay, so at that time again you will get the clear idea. Okay, then suppose we have two FDs, two set of FDs, that is F and G, then we'll say as a both are equivalent. Okay, maybe sometimes they are equivalent or may not. Okay, so we'll say both are equivalent when, that is, if F can inferred from G and G can be inferred from F. Okay, so there is nothing, inferred is nothing but whatever closure kind of things, whatever we are doing it. So here, so suppose I have as a two set. Okay, so first set is F. So in this, some FDs will be there. Okay, so consider as a F1, F2. Okay, so two are there, and one more set I have G. Okay, so in this I have something as a F3, then F4. Okay, so like this, four FDs are there. Okay, so suppose four FDs are there. So F1, F2, I kept it in one set, that is F. Okay, F3 and F4, I kept it in one set, that is G. Okay, so both are equivalent. Okay, if I can derive, that is from F, I can infer, that is these two FDs, I can apply the inference rules. Then I can derive F3 and F4 here only. So and same inference rules or different inference rules. Okay, so inference rules I can apply on F3 and F4, and I can get the F1 and F2. Okay, if I'm able to get it, so both are equivalent. It means, so you have F1 and F2 inference rules, so you can apply. So if you got this F3 and F4 both inference rules here, that is in F closure, if you got it, and G closure also if you applied, so in both all the FDs are same. Okay, so in both here, whatever we'll get it, so both all the FDs are same. So that time we'll say as a F and G are equivalent. Okay, so these two are equivalent, we'll say it. Okay, so this is theoretical definitions we are studying it in detail. We'll get the some examples also. Okay, okay, suppose if you're both are not equivalent. Okay, so if F plus and G plus, if both are not equivalent, okay, so it means one is greater than, maybe suppose F plus has a 5 FDs and G plus has a 4 FDs. Okay, so after some time, if you saw F plus if you got and G plus if you got, okay, so F plus has a 5 FDs and G plus has a 4 FDs, and these all 4 FDs are belongs to F, F plus. Okay, so it means F covers G. Okay, so here whatever is there, F covers G. So G is the greater one. Okay, so that is something but F plus whatever you have, more number of FDs are there in inferred rules. By applying inferred rules, you have more number of FDs. So here F covers G, we'll say it, not reverse one. Okay, G will not cover F because G has the less number of FDs. Okay, okay, what is minimal set? So minimal set we'll study after going for a normalization only. Okay.